Okay, so exponential growth decay formula. There's our formula. Now, there's lots of different formulas you can use. There's some that will do with money. This is one that kind of fits into all kinds of different places. There's other one where there's a different formula just for money based on the number of compoundings per year. But there's all kinds of variations you can do off this one for different growth and decay formulas that's exponential. But this is just kind of a standard one that we'll use for what we're doing here. So what we have again is A of t. That's the amount of money you have after whatever time it is you're working with. This is everything we've been doing so far. We've been doing functions. It's been f of x. But for this one, A stands for the amount and T stands for time. So it's still f of x, but in this case, it's A of t. It's the amount of money after time. So in that case, that's what they're going for. Again, A is your principal, which is your starting money. R is going to be your rate, but again, it's going to be your rate. You have to change it to a decimal, so you can punch it in the calculator and work with it. And T is going to be your time. All right, so the question is, if you invest $7,000 for 20 years at 4%, how much money will you have?
What is the L stand for, or is that a 1?
That's a 1.
Okay.
Yep. So it's 1 plus the rate to the T power. All right, so when we're going through these, the starting amount is $7,000. Time is 20 years. And your rate is 4%. And remember, when you change it to a decimal, basically you have to move it over 2 places. So if there is no decimal there, then we're understood that that's 4. Your decimal is there. Move it 2 places to the left, and that's going to make it 0.04. So that's your 3 numbers that you can be plugging into the formula. Okay, see the amount. So in that case, your T is 20. So your A of 20, which means after 20 years, this is how much money we're going to have. It's $7,000 times 1 plus 0.04 to the 20th power. Okay, and this is where it ties in with the exponential part of what we're doing yesterday, because this part you have to have a calculator, because without a calculator, unless you're just a true genius, and you can do 1.04 to the 20th power in your head, then by all means go for it. And again, the good thing is with any decent calculator, whether it's Casio, whether it's a Texas Instrument, doesn't matter what it is, if you punch that in on the calculator with parentheses just like it is, you don't necessarily have to do this part. It should give you the answer that we're looking for here. So we've got 7,000 parentheses 1 plus 0.04, and then we're going to raise that to the 20th power. There you go. $15,337.86. And the big thing is when you're going through these problems, you have to wait until the end to round everything off. Yeah. But this one's pretty much the calculator is going to do all the work for you on these parts of it. Okay, so on the Texas Instruments, if you've got the 1.04, that's your power button. Is this little rooftop button here? That's your power button. If you're using the Casio, yeah, there should be a power button that's there. So it would be 1.04, and there's your power button right there, right beside the X squared. So you hit that button, and then it lets you know you got your 20th power. And we multiply that by 7. Okay, so stock market. This is one of those things where, again, if you're thinking about stock market stuff, 4% is a very, I don't know if that's a low rate, but it's, a lot of times the stock market's going to do a lot better than 4%. Now, again, you get dips and turns where, back in the early 90s, I think we had a recession. We also had another recession about the time y'all were born, 2008, because the economy tanked huge at that point. But any other time, most times, you're going to get more than 4% growth on that one. So, this is just kind of a sample of what we can see there. Okay, so that's for our investing over a certain amount of time and doing this one. The second formula we've got to show you. All right, second formula is we're going to do continuous compounding. And this one looks a little different, and we'll use a different button on the calculator. All right, so this one is A equals P e to RT. Now, A is still the amount of money you have after time. P is your principal, your starting money. Per R is your rate as a decimal. And T is time.
Oh yeah, while we were on
All right, so for this one, let's give you some numbers so we can kind of run through this and see, and we'll show you which button you're going to use on your calculator here. So let's say that we have, oh, sorry, too far. So let's say you invest $2,000 for 6 years. At 5% interest. And they will have to tell you how it's compounded, if it's compounded continuously, or they will give you, whatever. Basically, they should, in the homework, they will give you the formula for these. So you don't have to worry about memorizing the formulas because there's all kinds of different formulas. Same thing on the test. Test will be the same way. You won't have to memorize the formulas. You just need to make sure that you know which one's which when it comes down to it. Okay, so if you invest $2,000 for 6 years at 5% compounded continuously, how much money will you have? Okay, so you do not have to worry about memorizing the formulas, especially this formula, because again, there's a million different variations of that formula that you can use. There's even a different one for doing this kind of money that you can do based on the number of compoundings, which we don't worry about it in this case because they pick a different one. So we'll give you the formula every single time as you're going through these. Okay, so there's the formula and there's our problem. So if we start pulling out the parts and pieces of it here, our principal is $2,000. That's our P. Okay. Our rate is 5% and our time is 6. Okay, so a little bit shorter formula. And this is one of those that the other one you can, for the other formula we have for the exponential growth decay, you can plug that in on just about every calculator and do this one. This one, when you use this formula, you might have to do a little bit of work in between just because of how it's set up and what it's going through this thing. So for this one, I would say the first thing you would want to do is where you got the RT formula, part of it here, go ahead and multiply those two numbers together. Because depending on the calculator you have, it might do that correctly, but it might not. So I would say for this one, go ahead and do the 0.05 times 6, which would be 0.3. Okay. All right, and then you can plug that in your calculator. Now for your E button, and all the E buttons are always tied together. And to find your E button, find your LN button, which on the Texas Instrument is right here. For the Casios, it is right there. So Texas Instruments here, Casios, it's normally right here. If you notice behind the LN button, right on top of it, you got this E button. That's your E that you have to use for this formula. So on this one, we'll do the Texas Instrument here. It's 2,000. You're going to hit second and then hit the LN button to get the E to show up. And then you're going to put in 0.3 there. Now this one actually you could do the 0.05 times 6 and close off parentheses and you'd be okay there. So we get 26.99.72. Okay, so we'll do that one more time. So if we go 2,000, You're going to hit second and then hit the LN button, which will then bring up the E or shift. Yeah, depending on which calculator. It's second or shift, whatever that top in the Casio. Yeah, it's the shift button. We'll do the Casio here in a second. And then you can do 0.05 times 6 if it gives that set of parentheses, which the Texas Instrument will do that and get you that number. Yeah. All right. And for the Casio, going through it real quick, it is 2000. Again, there's your second. Hit your E button. And that one, same thing. You do 0.05 times 6. So that will leave it, as long as it leaves it in the exponent, it's okay. 2699.72 if we round it off. All right. Just so you can make sure you know how to use your calculator. I may ask you to find e to the second power. And that will be some of the homework questions. May even be a test question like that. That you've got to know how to use your calculator. So if you put in e to the second power, what do you get?
E to the second?
Yeah, e to the second.
7.38.
Yeah, you get 7.389. Something, 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 something.
Yep.
Okay.
7.38905.
Yeah, and we'll cut it off to 3 decimal places. That seems to be a good spot now. It might even be that it might be something like this. It may be even e to the square root of 5. That you've got to be able to just kind of work with your calculators. So if you do that one, if it's second in e, and then we'll do square root of 5. You're like 9.356.
Mine is this syntax.
Again, the Casio works a little bit easier. So square root of 5. There we go. So we get something like that. So everybody good with your E button on your calculator?
I think so.
Okay.
Yeah. So are we done?
All right. Okay, so that's moving on from the E powers. So here's the new thing we're going to do. Logarithmic, which we're not going to call it logarithmic because that's a big word. So for short, we're going to call them log functions.
Is this note 15 or 14?
Let's just stick with 14 on this one. Yes, we're doing log functions. And if you notice on the calculators, right beside the LN button is the word log. So that's the button we're going to be using when it comes down to this part. Okay, here's the big thing with log functions. Log functions are inverses of exponential functions. Okay, so everything we were doing yesterday was exponential functions. Today we're going to kind of switch it up and we're going to do log functions. And here's the big thing today. Today is just a thing of making sure you visually can see it and understand it. So we'll move as quick as we can through it. Tomorrow we're going to come back in and work on it and do more stuff with it. So today it's more of just being able to rewrite it from one direction to the other to make sure we're good. All right, and remember the big thing we're talking about inverses. And we did this just a little bit in the last section. We're doing inverse of functions. The big thing is with inverses that you're going to switch the x and your y variables. So when you're thinking inverse, remember, we're switching your x and your y values when it comes off this thing. All right, so here's your visual. Here's what we're looking at for the log functions or log equation. If it's a log equation, it's y equals log of x. And they're going to put the base down here at the bottom, so it looks like that. And you can read it a couple of different ways. Most people will say it's log 4 of x. Some people say it's log of x base 4. You've got to tell what your base is, basically, when you're reading these questions. And if it's a function, then instead of being y equals, it's just f of x equals. Okay, so and again, there's really no difference. It's y equals, it's f of x equals. It's still the same thing. The main thing is you're working with this part over here. That's log of x base b, or again, it could be log b of x or something. So it could be log 4 of, x or something like that. All right, and the big thing we're going to do today is we're going to make sure you're comfortable just going from one form to the other form. And if we get comfortable with that today, tomorrow we'll bring this back in and we'll do a little bit more stuff with it. So it's more of just making sure that you can kind of get the visual of everything that's happening today. Okay, so here's what we're going to do. To write an exponential function, or and again, function or equation doesn't really matter what it is. We'll probably actually do more equations because of because if it is a function, the first thing we're going to do is we're going to take the f of x out and replace it with y. So really, let's just look at more equations. So to write an exponential equation in log form, you're going to add the word log because you have to write it in log form. You have to have that, and then you switch your x and your y. And the one thing that's true for both of these parts is whether it's in log form or exponential form, the base will always stay the same. And again, the big thing we're going to do today is we're just going to be able to have you rewrite it, because once we can rewrite it, then tomorrow we can rewrite it and then work with it and simplify and actually find out some numbers that go with this thing. But we have to be able to rewrite it today. All right, everybody good there? Everybody still writing that down? All right. So let's do this. Let me actually just give you some examples where we're going to rewrite it one way, and then once you're okay with that, then we'll turn around and go the other route so we can rewrite it the other way. So let's change this problem we have. Let's take something in exponential form. We're going to change it to log form. Okay. And they always start you off with just a basic where there's not any numbers to this thing. If it's exponential form, remember what we were doing the other day was we were basically doing this, that was some number, some base to the x power. And then, if this was 2 to the x power, 3 to the x power, like we were graphing yesterday, that was going to be y equals or f of x equals, we said we're going to make it equal y in this case. Okay, so to put it in log form, the very first thing you have to do is write in the word log. Okay, now this one's got the easy way. So over here, what was our base? The base is b, right? Because b stands for base. So over here, when you have this base, when you do a log, that base, that same number will go there. And then basically you switch the x and the y. It looks like the x is the exponent with the base here. Over here, now you're going to switch it. The y looks like the exponent, and then the x is going to be by itself. Okay, and you may be saying, why are we doing that? Tomorrow we'll show you why and how to use your calculator to be able to solve this thing. But today we just got to make sure that you're okay rewriting. All right, so let's give you something that's got some actual numbers on here. Let's say we're doing 6 to the x power equals 36. And they ask you to rewrite it in log form, which again means you have to got to have the word log in there. Okay, so over here, what is your base? It's 6, so the 6 will go there. And then you just basically swap these two numbers. The 36 will go over here, and the x goes over there. And you may be going, well, that's easy because I know that because basically what we're going to eventually do is we're going to solve for x. And you go, well, that's easy because I can do 6 squared equals 36. I know that x would be 2. Okay. But we're kind of building up to some numbers that won't be quite as easy. So let's say you have x to the 4th equals 81. And again, have you rewrite it in log form. Okay, the base is x, right? So the base there will also be x. And then technically these are your x and y values. So then for these two numbers here, we're going to switch these two numbers. The 81 will go there, and then the 4 goes there. Okay, so let's say we've got 13 squared equals 169. All right, now we have the word log. And again, the main thing is figure out what your base is. In this case, your base is 13. So over here, your base is 13. And then you just have to know that the other two numbers you have left over, they're going to switch. The 2 is connected to the 13. Now the 2 is going to be by itself. The 169 was by itself. Now it's connected to the 13. Okay, now sometimes they get a little sneaky because we're doing all these the same way. Let's change it up just a little bit here. Let's say you got 1 equals 3 to the 0 power. All right, we know we've got the word log. And again, on the left-hand side, what is the base? Or which one has the exponent on it? It's 3 to the 0 power, right? So 3, in this case, 3 is your base, right? So if they rearrange a little bit, you may have to kind of go for this part of it. So in that case, your base would be 3. And the 0 was attached to the 3. Now the 0 is by itself. The 1 that was by itself is now attached to the 3. So sometimes you got to kind of rearrange the order just a little bit when you think about it there, that you've always got to find the exponent, and then whatever's with the exponent, the number with that is the base. So then we know the base then would be 3. All right, now, and I don't know that we'll do a whole lot with graphs, but in a minute we'll show you one just to kind of get you through that one. Okay, so there's exponential log form. Let's go the opposite way in this case. Let's rewrite the log expression in exponential form. So now we're going to rewrite the log in exponential form. All right, so let's say we're doing log base 5 of 25 equals 2. Again, depending on who reads it to you, they may say log of 25 base 5 equals 2. So you can kind of go either way there. All right, over here, base is on the bottom, right? And to me, this is the one that's really easy because you just cover up the word log. The 5 stays where it is, and then you just switch these two numbers. The squared goes here, then you put the equal, and then you put the 25. So log to exponential, to me, is kind of the easier one of the two because you take out the word log, the base will stay the same, and then you switch these two numbers. So now it's 5 squared equals 25. Okay, let's throw a couple of variables in there. Just make sure we're okay. Let's go log of 2 base x equals 4. Or log base x of 2 equals 4. Okay, again, Base is easy because base is on the bottom, and then you just switch these two numbers.
Would we ever have to solve it? To figure out what?
Yeah. That's coming tomorrow. But the solving will actually be, if you can rewrite it, you can solve it. Basically, what we'll say. Most cases, there may be a few where you might kind of think your way through it, but most of the time, if you can rewrite it, you can solve it. All right, so we got log of 36 base 6 equals x, or again, log base 6 of 36 equals x. Again, base is at the bottom, so we know that's 6. And again, just switch these two numbers. All right, and then the one last thing. Okay, because occasionally you will get some problems like this where you do not have a base. So if a log doesn't have a base, then the base is 10. Okay, so anytime you're working with a problem, if there is no base there, they're just assuming that you're going to know in that case the base would be 10. So if you have a problem like this, it really means that it's that. So then if I ask you to rewrite it, it's 10 to the second power equals x. Okay, and Emma, to ask your question, that's some of the problems that you would have to wind up solving, because if you have this problem here and you don't know what it is, you rewrite it and you go, oh, well, x equals 10 squared, so then I know that x would be 100. You do something like that. Okay, and then really quickly, let me just show you what a graph looks like. We're not going to do a lot with it, but let me just show you what it looks like. Is everybody good? Everybody still writing that down? Okay, we'll pause for a second. Okay, and the graphs that we're going to do, because they're inverses of what we did yesterday, they actually look kind of similar to it. Again, we're not going to do a whole lot with graphs. So it's the main thing, just knowing the basic shape of it. So we're talking about graphs of log functions. All right, now what did the exponential function with growth yesterday? What did that growth exponential function look like? All right, we went upwards to the right, so we had a graph that looked something kind of like this, correct? This was b to the x power where b was greater than 0, or b was greater than 1. Okay, that was our exponential. This main point was at 0, 1. So if we do the inverse of it, instead of going through 0, 1, we're going through 1, 0. And instead of chasing up the y-axis, now we're going to chase up the x-axis. And instead of bottoming out on the x-axis, now we're going to bottom out on the y-axis. So it's the same graph as yesterday, but just it's inverse. It's flipped around. Instead of going up the y-axis, now we're going to go up the x-axis. Instead of being 0, 1 as a reference point, it's going to be at 1, 0. And if that's the case, so we're doing log of x and b as our base. Again, the one thing we're going to do for this one is that that's the base greater than 1. That's our growth, if you want to think about it that way. And since we're going to flip-flop everything, we're going to flip-flop our domain and range because all we did was we switched our x's and y's. Yesterday, the domain was always infinity to infinity. Today, that's going to be in the range. Now, this thing stops at 0 when we move to the left, so this is going to go from 0 to infinity. So we're just switching those values. Yesterday, it was reverse of this, but because it's inverse, we're just switching these values up here. Okay, so if I ask you to graph this one, and we might actually graph it, we'll just do this. What's going to happen with the minus 5 that's on the inside? Guess what it's going to do? Yeah, it's going to go 5 opposite horizontal, right? It's going to move it 5 spaces, not to the left, but to the right. And then the plus 3 means we're going to move it 3 spaces up. So the how you move and shift the graphs is still the exact same thing. Anything on the inside of the, in this case, it's going to be parentheses, is an opposite horizontal movement. Everything on the outside is going to be your up and down. So the shift, the movements, the transformations, they're exactly the same setup. It's just, now we're using the word log instead of it being x squared or x to the third or what it was doing. But it's still that same thing. Anything on the inside goes left and right. Anything on the outside goes up and down.